Thank you all for joining us for the NAIRR Artificial Intelligence Research Resource NAIRR Pilot Project Research Showcase, where our esteemed panelists will share insights into their cutting-edge work, motivation, challenges, and experiences. This event produces and provides a unique opportunity to connect with leaders in the field of AI research and education, making it ideal for individuals of all skill levels who are interested in the AI advancements. The showcase would also, highlights, group of panelists with representatives from NAIR initiative present to answer questions and provide an overview of the pilot project. With that, I will basically, I'm Nitin Sukija, and I'm the part of NAIR Pilot User Experience Working Group, in addition to Alana Romanella and Shelley Canute and Marisa Brazil. And I'll be a host for this panel and showcase. So we have our panelists here. I would like to thank again for the time. I know everybody is, busy and summer starting in every school. Thank you all for joining, especially with your extreme, crazy schedules. I'll say that. Our first speaker is Dr. Kimberly Elenberg. She is a response analyst with 19 plus deployments, 10 years of executive leadership experience, and a flair for algorithmic thinking. Currently, she is a principal scientist with Carnegie Mellon University Robotics Institute, Art and Lab, and the director of Data and ML AI Strategy National Security Intelligence for ECS Federal. She was previously aligned to the Department of Defense Chief Digital and Artificial Intelligence Executive Enterprise Analytics Support Directorate as a principal strategist for incident response, providing direct support to Secretary of Defense, Deputy Secretary of Defense, and the chairman and combatant commands. She led the development of 47 algorithmic planning application mission partner collaboration environments in support of Afghanistan NEOs and Ukraine foreign security assistance. With that, I would like to welcome Kimberly Elenberg, and thank you for joining us, Dr. Elenberg. I know, let me start sharing your screen and your slides. Give me a minute.
All right. Thank you very much. Appreciate it. So while we're waiting for the slides to come up, I just want to take a moment to really express my gratitude for the support that we've gotten from NAIRR. What project I'm going to talk about today is the autonomous robotic triage for mass casualty response. I think this graphic does a little bit of a good job just stimulating the imagination, whether it's a natural disaster or it's a battlefield. It could be civilian, military casualties. It doesn't matter. It could be something industrial. We just had in the news recently where there were a number of people who have been injured in a couple of industrial accidents across the country. The idea here is how do we both protect responders that are going in to buy them time so they can don personal protective equipment, and three, identify the casualties, their injury pattern, and the life-saving intervention needed very quickly. Next slide, please. So who are we? We are Carnegie Mellon University. We also have our subject matter experts from Pitt with us. Lockheed Martin is works with us with their Indigo drones. We use a bunch of other different drones and platforms. You can see our Boston Dynamics spot on the ground there. We have Starlings. The bottom line is what we're building is the payload that goes on the platform. Just like there's different types of cars for different types of things that you want to do, right? You wouldn't take a beetle to, or a bug or some small car to go pick up mulch, right, for a farm. You would take up a pickup truck. And likewise, you wouldn't want to drive your pickup truck into New York City, right? You would want something smaller. So depending on context of a natural disaster or a battlefield, you would want to have a payload that can do the job that you need. So the focus for the NAIRR project is on the payloads that are actually on these platforms and the data that those payloads capture. We're in year 3 of 3, so we're coming up on our final competition, and we could not have done this without PSC. Go ahead to the next slide. So when a disaster occurs, we have something called the platinum 10 minutes and also the golden hour. That being said, if you're in a lot more remote areas, it could be 72 hours before someone gets to you. I think folks are following right now. There's like 5 people trapped in a cave that they're trying to get to that are, pretty hungry. So, we're looking at not just can we identify where those casualties are at, what their injury pattern is, and the life-saving intervention needed, but how do we start to make sure that data is going to be available so we would know how to extract them? And so, a part of what we do is thinking about that human-machine teaming. And as this slide indicates, the number of responders that are exposed before the scene is assessed could be zero, right? We have the opportunity to put and integrate chem, bio, rad, nuke sensors onto our platforms. They also help us with identifying injury pattern. And the scenario types could be infinite. So this could be a dual use product that could be used in any industry that is needed. Okay, next slide. Okay, so what NAIRR helps us with, number one, accelerating discovery. The complexity of our models is huge. So if we have 10 different platforms and each one of those platforms has a payload with possibly two payloads with multiple cameras, now you have full motion video, you have other data that's coming in from these multimodal sensors that you have to make sense of, right? And in order to do that, we have to train our models that help us with that. And we use a VLM and then a Bayes net for probability. So in order to train our VLM on all this data that's coming in, we definitely need the capacity that the NAIRR program yields for us. It really gives us a great environment for collaboration across the workforce. And, we can trust in the security of that environment, which is really important because a lot of our data is PII data, right? It's off of individuals. Next slide. So this is kind of saying, a summary of our approach, right? We sense, we make sense so we can act, right? And we have to do this and orchestrate all of this inferencing on the edge. So some of the other things we're trying to do is make sure that our models are compressed and that we have a resource allocator so that we can work within the bandwidth that we have, which could be limited in a disconnected environment when the cloud is not available. And if you think about disasters, certain times maybe cloud will be available, maybe sometimes it won't, and sometimes it could intentionally be jammed. So we need to think about that so that we can make sure that all the data that we do collect can get to the appropriate echelons at the right time. So meaning maybe you have point of care data, and eventually you want to make sure that data is getting to the hospital, and maybe they need to go up to higher level care hospitals, and so you would want that data to follow the person since it's their data. Next slide. Okay, so these are some of the contributions to science that are coming out of this. This is our autonomy and perception that works in the field. So we found that a lot of our autonomy and perception works very different inside than it does when you are outside. So making sure that our spot can actually navigate that quadruped without running over anybody is a big deal. And especially when it's in a dynamic environment that's intense because it's an emergency response, and people are just running around a little bit like a chicken with the head cut off. So we have a lot of our drones advancing towards autonomous building entry. So not only can we fly, not necessarily autonomously using waypoints, but can we fly dynamically in changing environments and oh, can we identify openings within a building, whether it's a window or a hole in the wall or something, so we can go into that rubble. That's super important, especially after something like an earthquake. Next slide, please. Some other contribution includes some of the specialist models. So heart rate and respiratory rate, if you're wearing a sensor, it gets picked up really well. But what if somebody doesn't have a sensor on? What if this is in a third world country or something like that? Or on a battlefield where people don't want to wear sensors because they don't want to be detected or things like that. We've taught these models how to pick up heart rate, respiratory rate, hemorrhage, alertness, all the things that a medic would do, but using different tools. So it doesn't work. We can't use exactly the same algorithms that a human does because there are things that a human has, like skin and to touch a person. They have the ability to roll a person over, all these different things that a drone flying over a scene doesn't have. But a drone flying over a scene might have the ability to see in the dark because of thermal, or might have the ability to see heartbeat based off of color changes in your eyes that a normal human eye can't perceive. And so we build these different models because the ones that are on the shelf that they're using in hospitals don't work in the wild. And so we're building them. And then, like I said, we're building the vision language models to take all of those different data segments and kind of make a scene like you would in a movie, so you can have context and then come to, given the context, the higher probability of identifying the injury pattern that would make sense for what you're seeing. And so we're doing that. And then you can see here that this becomes very important. Again, tying it back to the ability to train this. Just like an LLM, a VLM can be confident and wrong. And so, as we're training these, we're measuring accuracy against ground truth so that we can fine tune those models. And that's very helpful for us. Next slide. Some more contributions are some of the calibrated decisions, right? We want to make sure that the human who's receiving this information has the confidence in how reliable it is or is not, so that they can decide to either move forward without the tool, if they think that's going to save more lives, or if they have confidence in the tool, with the tool in a manner that will be more efficient. So, we're trying to do that using some traditional statistics, which is our BaseNet, and, treat things as a probability, not necessarily a hard fact. Next slide, please. So some of our measurable progress to date. This one shows us how much autonomy among the swarm we have achieved. So, again, we have the 10 different platforms, and end to end, there's 4 different gates that we're doing this in. So gate 1, for example, is, can we find the casualty and how accurate are we? And can we do it autonomously? And you can see we're achieving that at 75% right now, 75% autonomy. We're at 62% autonomy in one of the harder gates, which is gate 3, which is our heart rate and our respiration rate. And then our data labeling is clearly improving. And we test this weekly as we make our changes, as we fine tune these models. And so, some of our deliveries include, pipelines that have providence, so that, again, you have confidence in the data, where it's coming from, and the accuracy of the outputs. Next slide, please. So we've used a lot of resources. I think we request resources all the time, because these are hungry models. It was funny, CBS came out to visit us and they wanted to give our quadruped a dog biscuit. And I said, well, Spot doesn't eat biscuits, it eats batteries, right? And it was really cold. It was January. So we were just going through those batteries. So, we're trying to really think about that resource management. How do we do that so we are responsible in what we're consuming? And how do we do experiment management? And I think, this is something I'm very proud of the team for, right? This is an ethical thing because we do know that, consuming this greedily, right, means that resources might not be available for others, right? And we share our resources across our research community. And so, we have to think about that. And I really appreciate working with the Pittsburgh Supercomputing Center and their guidance on that. They've been amazing with helping us think ethically about this sort of thing. Next slide. As I was alluding to previously, we want to make every GPU count. And some of the ways that we do that, you can see on this slide, right? Where, we have a central orchestrator, we're using uniform REST APIs, we have our testable pipeline. So, the cross model API library, that is completed and handed to the VLM orchestrator is one very important thing to help make every GPU count, especially because we're executing this part of it on our platforms at the edge. Next slide. So this is in some ways a little bit of a summary of the hard problems that we're solving, right? So the GPU contention, obviously we've talked about that. Federated validation, this is definitely needed for the workflows and the dynamic scheduling of our resource allocators, right? We're really looking, like I said, at if we are doing our compute at the edge on a disaster, and if anybody lived in New York during 9/11, you'll remember communication was severely affected, right? So, that's something that happens in disasters. So that's something we're contributing to. Um, we want to make sure that we're confident. We assume we're confident, but may not be right. So what is the probability so that that human machine teaming can be respected? We're really thinking about the residual duplicate detection trace to the map drift. So this is really we want to, the more precise we are, the better we can score. And if you start thinking about this mathematically, like from a GPS perspective, we might be off by 2 meters and by time by 3. And then if you have all of those frames, this becomes a geometry problem, like a major geometry problem and other sorts of things. And we start to consume a lot of data. So next slide. So we do definitely want to keep engaging. We want to publish and share. Whatever we can have as open methodology, we want to do that. Um, we definitely want to showcase this mission. I think anything that helps with saving lives, people can get behind. This is like a really good thing. And then, for training the next cohort, we certainly plan on, bringing on students and doing follow-on work with DARPA. Next slide. So this is our road to November. You can see we are in the thick of June. We are going to be arriving on site for this final event, October 28th. And God willing, we will be performant and we will have the opportunity to put this in the hands of emergency response personnel and in short order. Next slide, last slide, I think it is. Yeah. So in some, faster triage, safer responders. I lost a lot of friends during or as a secondary result of the exposures during 9/11, and that was a really sad thing. I don't want to do that. So if we can save both casualties and we can make this safer for responders, that would be truly a blessing. And again, thank you very much to my team. At Carnegie Mellon, at Pitt, Lockheed Martin, Booz Allen has helped with the ATAC stuff. We've had Bosch who sponsored us. So many people I can't even say. But for all of our sponsors, thank you very much. And to NAIRR for supporting us, we are very grateful. And with that, I will close because we are at 2:20.
Thank you so much, Dr. Elenberg. Really appreciate your, coming here with your, heavy schedule. I can see you're still, in between, and we appreciate your, time and efforts, especially with the different projects you're performing. Thank you again, from everyone. Let's move on to our next speaker, Dr. Huirong Fu. Dr. Huirong, you can share your screen, and meanwhile, I can introduce you. Dr. Huirong Fu is a University Distinguished Professor and founding director of the Center for Cybersecurity at Oakland University, where she serves as NSA CAEC, CACD, and CAER point of contact and leads institution efforts in AI-driven cybersecurity research, education, and national coordination. Recognized expert in AI, autonomous connected vehicle security, and AI-enhanced cyber defense, she has served as a PI or PD on numerous federally funded initiatives, including NSF SFS, Bridge to Cyber, RU in Cyber AI, and National AI Resource in NAIRR Pilot, multiple NSA and NSF SIN cyber programs. Dr. Fu has extensive experience directing complex multi-institutional consortia, most notably as a lead PI of the National Workforce Initiative, driving autonomic industry workforce transformation, AI, and cybersecurity, DRIFT. With over 100 peer-reviewed publications, 13 graduated PhD students, and more than 100 undergraduate researchers mentored, and she brings deep technical expertise and demonstrated leadership in advancing AI and AI integrated cybersecurity at scale. Thank you so much, Dr. for joining us. With that, it's all yours.
Thank you. So could you see my share screen?
Yes, we can see your screen. If you can make it,
Yeah, awesome. Thank you. So today it's my great honor and the pleasure to introduce our project funded by NAIRR Pilot project. And here's the title, Collaborative Research in 3 areas, advancing AI research in cybersecurity, edge AI, and autonomous driving is a collaborative project between Oakland University and WPI. And so the funding numbers are OAC 22, yeah, as shown over here. So for this project, we do research in these 3 areas. And then we also developed 12 workshops and for training of the workforce. And in particular, it's a 2-year project. And each year we host a 12 workshop training in terms of how to use the NAIRR resource for the 3 areas, cybersecurity, AI, and autonomous driving. And we also provide the supporting all the development materials, including the code hosted by GitHub, case studies, and so on, and also including the video recordings and the slides. So every other Saturday, we host a workshop for 3 hours each, from 11 a.m. to 2 p.m. Tomorrow, we will host the number 6 workshop for year 1. And also we provide the asynchronous support, including the YouTube and also the discussion forums. And yeah, so the motivation, in particular, we focus on the cybersecurity area. And because cybersecurity, we need AI, and also we need the GPU-enabled AI, for example, LLM, and as adversarial machine learning, so on and so forth. So for our project, we have 4 themes. The first one is introduction to use the NAIRR and navigating its resources. Then theme 2, 3, 4 each has a focus area. Then theme 5, we will have the combination of onion 2 or onion 3 of the themes 2, 3, and 4. So for theme 1, we're focusing on the how to use the NAIRR, and we are very lucky and fortunate to work with JetStream 2, the GPU resources hosted by Indiana University. So we provide the training with the workshop So in terms of how to navigate the resources, the workload in terms of the GPU, CPU, cloud services, how to set up the accounts, how to configure the environments, and validate the end-to-end access, and how to perform the data sites and with the AI workflows. And in particular, here are some tools and platforms we will go through and help the participants set up their environment. So by the end of the first workshop, the participants will get to, learn and familiar with the notebook-based labs with metrics, stand up working on the AI workflows and integrating the AI models, and run a baseline experiment and live with reproducible starter environment. And then SIM 2, AI for cybersecurity and trustworthy AI. Then Edge AI, then AI-powered autonomous driving. And here's a big picture. So in total, we host 12 workshops as series, but the participant can participate in any one of them or participate in all of them. So the first one is introduction. The last one is a takeaway. In between them, we have 2 related cybersecurity and 2 related to Edge AI and 2 related to autonomous driving. Then between them, we have the combination of any combination of 3 of these 3 domains. So here are some example modules we developed AI for cybersecurity. Yeah, due to time limitation, I will not go into the technical details. And then security in AI. And AI-enabled sensing and control. And here's a big picture about the 5 workshop series and also the corresponding computing resources. In particular, we are right now using JetStream 2 GPU. And here are the example data sites that have been integrated into the different workshop with the corresponding SIMs and also the corresponding AI development and deployment tools. So yeah, here shows what the computing resources have been used and requested. Once again, with Indiana University JetStream 2. So they support both CPU and GPU. Yeah, here shows, and the example, we have 50 instances and 75 volumes and 16 public IP addresses that have been used so far. And so far, it has supported 9 projects and 7 posters, 6 attribute papers that have been published, and also 4 workshops posted, including from high school to undergraduate students through the NSF-funded research experience undergraduate program, and also other undergraduate students, 10 graduate students, and 10 faculty members. So far we have hosted 5 workshops, and including 89 faculty, 99 master, 65 PhD, 58 undergraduate, and here shows the number of participants per workshop. And in particular, here gives the more information about what workshops we have hosted. And tomorrow we will host the number 6. And for each of the workshop, we have the GitHub repositories. So they have been made available to all the participants. And also we have made the YouTube, the video recording available via the YouTube, and also the slides available for the faculty or for the graduate students to reuse. And so the workshop is still open for application and participate. If you have interest, I will share the QR code at the end of today's presentation. And well, the challenges, as listed here, scalable resource allocation, participant onboarding, software installation and dependencies, and the technical troubleshooting in real time. So to overcome these challenges, in collaboration and also with the help with the Indiana University, we deployed Jupyter Hub. So it's a small user, it's a multi-user server designed to deliver the Jupyter notebooks to groups of users, and it manages authentication and spawns individual notebook servers for each person during the workshop participation. It provides a consistent computational environment without requiring users to install the software locally. So in this way, it's much easier for us as the workshop provider and also for the workshop participants easily follow us to get the hands-on experience within the 3 hours per workshop. So, well, for example, right now, 1, 2, 3, 4, 5 workshops have been deployed under the Jupyter Hub solution. So scalable and so with the Jupyter Hub, it's scalable, and it can support right now up to 80 participants per session. And also its sustainability with the GitHub repos, the code, slides, and everything. Yeah, acknowledgement. Once again, this project is sponsored by NSF and is sponsoring 2 collaborative universities, Oakland University and WPI. And also it supports our 2 other programs, the NSF Scholarship for Service in the area of cybersecurity workforce training, and also NSF sponsored research experience for undergraduate students sites last summer and this summer. And yeah, here is besides the NSF projects, we got the NAIRR resource through this grant number, and also with the support in collaboration with JetStream 2 from Indiana University. So if you have interest in participating in the workshop training, here is the link, the QR code for the registration. And this workshop is limited to any researchers who are participating in the US-based universities. And all the resources are posted over here. And also the project website hosted by Oakland University and one hosted by NAIRR project. And here is our team, in collaboration between Oakland University and WPI. I'm the lead PI, and Dr. Dai is the PI from WPI. And here we have 8 or 7 co-PIs and more than dozen graduate students. And here are the RU participants of last summer. And this summer, we have 10 more undergraduate students joining us. And we will use the NAIRR resource again, doing the research. Thank you.
Thank you, Dr. Fu. We have one question for you. The question is from Jenna. The question is, what is the duration of the workshops?
Duration, awesome. So each time is 3 hours. So, but every other week on Saturday from 11 a.m. to 2 p.m., 3 hours every Saturday, Eastern time, we host one workshop. But each workshop lasts for 3 hours. So starting from March 21st through August 22nd. So if you have interest, please join us. So tomorrow would be the number 6. So we will host 7 more. Yeah.
Yes.
So you can, so this is, either scan this or send me an email. I will send you a flyer. So this is my email address. My last name, oakland.edu. I'll just scan this code to register. but once again, it's limited to the researchers US-based. Thank you.
Thank you, Dr. Fu. Just to give you a heads up, all of you, this seminar webinar is basically posted on NAIRR YouTube channel, so you should all be able to see the slides and the recording there. So if you have any questions, you can reach directly to Dr. Fu. With that, I think we have no more questions for Dr. Fu. We'll move on to our next panelist. Dr. Fu, thank you so much for your time. Really appreciate your expertise and your help with the community. With that, I'll introduce our next panelist, who is Dr. Zihan Zhang, who is not doctor yet, but I'll say this. I want to announce this because she is joining us. She's a PhD candidate in industrial engineering at Georgia Tech, advised by Dr. Jiang Shi and Cameron Panenberg. She'll be joining the School of Computing and Augmented Intelligence as a tenure track assistant professor at Arizona State University in fall 26. So congratulations. Her research focuses on system informatics and control, as well as engineering knowledge informed data analytics for high dimensional data with application in manufacturing, healthcare, energy systems, and agriculture. Zihan translated her research into a new graduate course model titled Tensor-Based Spread Modeling and Process Control, and has taught it twice. She is also deeply committed to community engagement. She co-founded the Informs K-12 Education Outreach and Networking Program, which received the 2025 Informs Volunteer Service Award. As president of the Informs Georgia Tech student chapter, she leads the organizations to achieve summa cum laude distinction and was honored with 2024 Informs Judith Lebman Award. With that, I would like to say congratulations, Zhang, for your PhD, and I'm glad I can announce it on the platform. It's all yours. You can share a screen and start. Thank you.
Thank you so much. Can you see my screen?
Yes, thank you.
Hello, everyone. It's our great honor to share our project, Real-Time Run-to-Run Control of Disturbance Propagation in Additive Manufacturing via Large-Scale Diffusion Models. This project is under my advisor, Dr. Jianjun Shi's proposal, and I'm the administrator for this project. So our project aims to use the diffusion models to learn how the disturbances evolve over time during the run-to-run control. So we focused on modeling the temporal evolution of the disturbances in complex manufacturing systems. So by learning the disturbance dynamics from the data, we aim to improve understanding, prediction, and potentially real-time control of the manufacturing processes. So our projects are focused around the run-to-run control. So what is run-to-run control? So run-to-run control refers to the control production run by run or batch by batch. And the production will be conducted continuously across different runs. Specifically within each run, we need to first set up the machine, conduct the production, then we will adjust the machine to prepare for the next run. Specifically within the teeth run, we will conduct the continuous measurements towards the system responses, and we will conduct the continuous control execution. However, since we need the time for sensor to collect the data, or due to the limited computational constraints, we may only adjust or change the control settings at the beginning of each run. So as we can see from this figure, we will only adjust the control action either at the beginning of the current run or at or to prepare for the next run and to adjust the control actions. So the question becomes how we can adjust the control variables to improve the product quality. So this project was originally motivated by the manufacturing process. Here we take the semiconductor lithography process, for example. Here we have the lithography machine. The lighting will be projected through a mask onto the photoresist materials on the wafer. Then the pattern will be generated layer by layers. Specifically, the misalignment between two adjacent layers is called the overlay errors. However, during the production, we have the disturbance which will influence our production. So for example, due to the temperature fluctuations, the two wear on length or the photoresist thickness variations across wafer, the overlay errors will propagate over time. However, we can adjust a few control variables to limit the overlay errors. For example, we may adjust the lighting source or to change the state position. Our goal is to minimize the overlay error with the target to be the 0. However, there are several challenges in order to handle such problems in the real production. As we can see for the disturbance modeling, the disturbance may have the nonlinear involvement. And based on the system measurement, we may have the high-dimensional images captured during the production, and also the disturbance involvement may have the spatial temporal correlation. As for the control execution, we have 2 time schemes. So we need to consider how we adjust or set the control actions within the run, or to adjust the control actions across different runs. And this project, we want to quantify the decision, the uncertainty of the decision making. So before our work, there are several previous works towards our goal. So very beginning, we may have the EWMA run-to-run controller, but they only handle the low-dimensional representation, and they assume the linear correlation structure in the disturbance. And also, we may have the tensor-based run-to-run control in the parse. Although they can handle the high-dimensional data, they assume the low-rank correlation structure in the disturbance. Recently, we also have the learning-based run-to-run controller. They formulate the system response as a nonlinear function of the control variables, but their methods is hard to provide the solid control analysis. We may also have the reinforced learning-based controller, but it's based on the trial and error, which is not suitable for the data scarce or the high-risk industrial environments. Due to the advancement of the machine learning or the deep learning methods, we now have the diffusion models by integrating the prompts. However, for the current diffusion model methods, they may not include the feedback loop, which is not suitable for the in situ industrial process control. For this project, we aim to develop a nonlinear spatial temporal run-to-run control framework, as well as quantifying the decision-making uncertainty. So specifically, our projects are around 2 stages, the offline stage and online stage. For the offline stage, consider we have a manufacturing process. So we have the input and the system response output. So based on the data, we want to build up a process model. As for the online stage, we need to develop a control strategy. Then by integrating the process model and the control strategy, we will set up a controller, which will provide us with the control variables. By inputting the control variable into the online process, we can generate the system output. Then we can close the loop based on the feedback. Specifically for this project, we propose to utilize or train the diffusion models to capture how the disturbance evolve over time, to capture the nonlinear dynamics and handle the spatial temporal correlation. And for the online stage, we propose an uncertainty-aware prediction control strategy to handle the control execution as well as quantify the uncertainty towards the control actions. So currently, we have already finished the deployment of our prototype work, which is designed for a lithography process using the synthetic data generated based on the simulator. And this work has been accepted in Technometrics. We are now working on the data generation in collaboration with UNIST from the South Korea to generate the data based on the real additive manufacturing siting. And we want to extend our prototype work to the larger scale real world additive manufacturing siting. And we plan to share our data set with the public audience. And also I'm now working on the follow-up work based on the additive manufacturing application. So the resources we have requested from the NAIRR is the GPU computing hours as well as the Whispers training platform. Throughout our project, we have met a few challenges. The major challenge is the high computational cost of the training diffusion models and tuning their parameters. Thanks to NAIRR provided resources, we can address these challenges. There are also a few more challenges associated with engineering problems. Specifically, we need to collect and organize the manufacturing data sets. And during the data organization, we need to ensure the data quality and the consistency across different experiments. And when we when we develop our new models, we need to capture the complex disturbance dynamics over time. And based on our current progress, we want to scale our existing model the developed model from a prototype to the real manufacturing applications. Looking forward, we plan to share our data sets once available, and we will continuously publishing our research outcomes based on the NAIRR supported work. And we plan to exchange the best practices on the AI model training, data management, and the computing usage. And we are looking forward to collaborating with other researchers working on the AI for manufacturing control and scientific machine learning. Thank you. We truly appreciate the kind support from the NAIRR pilot program.
Thank you, Zhang. We appreciate your efforts, and especially the materials you've gotten ready for the efforts. And I would like to I think open the floor for any discussion or questions from Dr. Fu or Dr. Elenberg, because we have 10 minutes or so on time. I don't see any questions for anyone. But I was going to give you a heads up, if you are, if you have questions about NAIRR pilot, please go to the website, and if you can submit a ticket there, and as soon as you submit a ticket, anyone will be in contact with you to help you and to make sure that we basically address your issues and there are any pain points you have in adopting NAIRR or NAIRR resources. And we want to make sure we are here to accelerate your research and your participation in the communities with respect to NAIRR pilot resources. I don't see any questions. I would like to thank again the panelists, Zihan, Dr. Fu, and Dr. Elenberg. And with that, no question. I think we're going to end early the webinar. So thank you all for coming, and then enjoy.
Thank you.
Thank you.
Thank you so much.
Bye-bye.
Have a good weekend. Bye.